Whenever a new Pro iPhone comes out, the marketing is always, it's always exactly the same.
Mm-hmm. It's the stuff that looks good on a billboard.
Totally. They show you the camera lenses, which are like the size of dinner plates now.
Yeah.
And they show you the titanium frame, and maybe they talk about gaming, all very surface level stuff.
You can't exactly put a schematic on a Subway ad and expect people to get excited about it.
Exactly. But I've been buried in this stack of documents you sent over, schematics, board layouts, all of it, and I realized we've been looking in completely the wrong place.
Yeah.
The real Pro feature, the thing that actually separates the high-end machines from the regular ones, isn't the camera. It's buried deep inside the logic board.
And honestly, it is a nightmare to understand at first glance.
It looks like a mess. But apparently it's a masterpiece. We are talking about a specific circuit today, a new hidden heartbeat for the iPhone that Apple introduced, sort of quietly, with the iPhone 13 Pro.
Right.
It has a name that sounds like a randomly generated Wi-Fi password. VDD SNS BPIC.
Rolls right off the tongue, doesn't it?
Beautiful. So welcome to the deep dive. Today, our mission is to decode that string of characters, figure out why Apple suddenly decided to completely overcomplicate their power delivery, and what this tells us about the future of our devices.
Because it's a big deal.
It is, spoiler alert. They physically split the brain of the power system in half.
Which was a massive shock to the repair community, to say the least.
Before we get to the shock, though, we have to establish the baseline. Because for years, power inside a phone was kind of boring as a solved problem.
It was very standard. If you go back to, say, the iPhone X or the iPhone 11, the power architecture was centralized. You had the battery, which is your fuel tank.
Okay.
And then you had the PMIC, the Power Management Integrated Circuit.
The PMIC, just one chip.
Right. A single chip. Think of the PMIC like a traffic cop standing in the middle of a busy intersection. Power comes in from the battery, and the cop just blows the whistle and directs it.
You go to the screen, you go to the memory.
You go to the Wi-Fi chip.
Yeah.
It was one boss giving orders to everyone.
Simple. And technicians knew this setup inside and out. I remember reading about chips named Tigris or Rubicon.
The usual suspects.
Exactly. If the phone wouldn't turn on, you went straight to the traffic cop.
Precisely. It was reliable, it was understood, and most importantly, it was all in one place.
But then the iPhone 13 Pro lands on the workbench. Technicians open it up, they look for that central traffic cop, and it's gone.
Or rather, it's been mutated.
Mutated is a good word. The rulebook wasn't just updated, it was shredded.
Apple moved from that centralized manager to what we call a distributed architecture. And the most jarring thing visually, the sheer amount of heavy machinery they added.
This is the 7-inductor architecture mentioned in the notes. Now, for anyone trying to picture this, usually on a phone board, you see these tiny little specks, maybe 1 or 2 gray square coils.
Those are the inductors.
Right, near a power chip. But here we're talking about 7 of them.
7 massive inductors. And you have to understand the scale here. Inside a smartphone, board space is the most expensive real estate on the planet.
Right.
Engineers fight over millimeters. If you want to add a component, you usually have to take something else away. So to dedicate space for 7 large inductors, that is a massive statement of intent.
It's like buying a studio apartment in Manhattan and filling half of it with a V12 engine.
That's a perfect analogy, actually.
You just don't do that unless you plan on going really, really fast.
You don't put a V12 in a commuter car. You put it in a race car. And that is exactly what the circuit is. But the layout is the first thing that really throws people off.
Yeah, let's unpack the split brain thing. Because you said it's not just one chip anymore.
No, they split the responsibility. We are moving from that single traffic cop to a highly coordinated team. You have 2 primary chips now, U4000 and U4200.
U4000 and U4200, okay. So in my head, I'm picturing them sitting right next to each other, shaking hands, passing data back and forth.
You would think so. Logically, that makes sense. Keep the traces short, keep the communication fast.
But this is Apple we're talking about.
Exactly. In the board layouts for the 13 Pro and 14 Pro, these 2 chips are often located on opposite sides of the logic board.
Wait, like physically on the back and the front of the board?
Yeah. Or separated by a huge distance on the board layers. Imagine trying to troubleshoot a circuit where the 2 main components are playing hide and seek.
That sounds absolutely maddening for a repair tech. You're diagnosing a power failure, and you have to mentally flip the board back and forth.
It just breaks your mental map of the circuit. You have to understand that even though U4000 is over here and U4200 is way over there, they are acting as a single functional unit.
So they're communicating through the floorboards.
through the layers of the PCB, yeah, coordinating this massive flow of energy.
So U4000 and U4200 are basically estranged lovers shouting through the walls.
But they work together beautifully, and they split those 7 inductors between them.
Right, let's trace the flow. It starts with U4000.
Yes. U4000 is the first stage. It handles 3 of the inductors. Think of U4000 as the liftoff stage. It takes the raw power from the battery, does some initial processing, and prepares the energy for transfer.
Okay, so it preps the meal, and then it hands it off to U4200.
Correct. U4200 is the heavy hitter. It controls the remaining 4 inductors. And this is where the magic really happens. This is where that complicated PPD DSNS BPIC line is actually created to power the phone.
And U4200 is the one doing the heavy lifting for the interleaving.
Exactly.
Okay, I want to double click on that word, interleaving. I saw it all over the schematics. It sounds like something from a sci-fi movie. Is this just marketing fluff, or is it actually doing something different electrically?
Oh, it is definitely not fluff.
Yep.
Interleaving is the secret sauce that makes the Pro phone possible.
Break it down for me. Why do we need it?
Okay, let's go back to your car engine analogy.
Mm-hmm.
Imagine a single cylinder engine, like a lawnmower.
Okay. Bumpy. Loud.
All right, it goes pop, pop, pop. Every time the cylinder fires, you get a burst of power, but in between the fires, there's a gap. The power delivery isn't continuous.
In electronics, we call that ripple.
Exactly. Ripple. And I'm guessing sensitive microchips don't like ripple.
They hate it. They want a flat line, a smooth stream of energy. If the voltage dips too low between the pops, the phone crashes. If it spikes too high, you can damage components.
For sure.
So how does adding 4 inductors on the U4200 side fix that?
That's interleaving. Instead of one big cylinder firing, you have 4 smaller cylinders.
Right.
But, and here's the genius part, they don't fire at the same time. They're phase shifted.
Phase shifted, so they take turns.
Precisely. Just as the wave from inductor 1 is starting to dip down, inductor 2 is peaking. And as inductor 2 dips, inductor 3 peaks.
Oh, wow.
They overlap perfectly to fill in each other's gaps.
So the ripple disappears because they're canceling out the downtime.
Precisely. It's like a V12 engine. The explosions overlap so perfectly that the power delivery feels like a continuous, smooth roar. You get this incredibly flat line of power.
Okay, smoothness is good. But the notes mention something else that I think is even more important. Transient response.
Yes, this is the real reason for the 7-inductor beast.
What does that mean in English?
It means speed. But not processing speed, reaction speed. Think about how you use your phone. You're reading a text message, the screen is static, the power draw is low,
All right.
and suddenly you flick your thumb to scroll. Instantly, the screen has to ramp up. Specifically on the Pro models, we have promotion displays.
They go from 10 hertz to 120 hertz.
In the blink of an eye, 120 times a second. That requires a massive surge of power. It's a transient load. The demand goes from 0 to 100 in a microsecond.
And the old lawnmower engine couldn't handle that.
It would choke. It wouldn't be able to provide the torque fast enough. The voltage would sag, the screen would stutter, or the phone would just shut off.
So this architecture is basically a dragster. It's built for instant acceleration.
It creates a power supply that is stiff and responsive. It can dump massive amounts of current instantly without the voltage dropping. That is why you need 7 inductors. You need that reservoir of energy ready to go at a moment's notice.
That makes so much sense. It's not just about keeping the lights on. It's about keeping them on when you suddenly flip every switch in the house at once.
Exactly. And doing it without generating a ton of heat. Which brings us to another crazy detail in here. The ghost resistor.
The ghost resistor. This sounded like wizardry to me. The sources said that usually to measure how much power is flowing, engineers put a physical resistor in the line.
Yeah, it's a standard technique called RSense. Think of it like a toll booth on a highway. If you want to count how many cars are driving down the road, you force them all to go through a single-lane toll booth.
Simple enough, you count the cars as they pass.
But toll booths cause traffic jams. In electronics, resistance creates heat. Every time you push current through that sensing resistor to measure it, you are wasting energy.
You're literally turning your battery life into waste heat.
Just to know how much power you're using.
So what did Apple do with the U4200 circuit?
Just bulldoze the toll booth.
They just took it out.
Gone. There was no physical RSense resistor in this circuit.
How do they know how much power is flowing? Don't they need to count the cars?
This is where the complexity of that U4200 chip comes in. Because the chip is controlling those 4 interleaved phases so precisely, it knows exactly what each inductor is doing.
So it can calculate it.
It can calculate the current mathematically based on the slope of the waves.
That is wild. So they replaced a physical hardware component with math.
Essentially, yes. It's called lossless sensing. They get the data they need. Current monitoring is critical for safety, but they get it without the penalty of heat or resistance.
That explains the efficiency. You save space, you save heat, and you get better battery life.
Well, you don't really save space. Remember, we added 7 giant coils, but you trade that space for purity. You are trading board real estate for the cleanest, most efficient power delivery possible.
Which really brings us to the Pro distinction, because I was looking at the compatibility charts in the research, and there are a lot of red X's next to the standard iPhone models.
This is a crucial distinction for consumers. We often assume that newer is better. You might think an iPhone 15 is automatically better in every way than an iPhone 13 Pro.
Right. It's 2 years newer.
But in this specific case, you'd be wrong. This 7-inductor, dual-chip architecture, is exclusive to the Pro and Pro Max models.
Only them.
It started with the 13 Pro, it's in the 14 Pro, it's in the 15 Pro.
But the regular iPhone 14 or 15, the ones most people buy.
They do not have it. The standard models still rely on a different, more traditional, simplified power delivery system. They lack this specific interleaved beast we were discussing.
So technologically speaking, the power heartbeat of an iPhone 13 Pro is actually more sophisticated than a base model iPhone 15.
In terms of power delivery architecture, absolutely.
Yeah.
And it comes back to that V12 engine analogy. The base models don't have the 120 hertz promotion screens. They don't have the extra GPU cores enabled in some generations.
So they don't have that transient load problem we talked about.
Not to the same extreme. The V6 engine works just fine for the standard commuter. Apple is ruthless about efficiency and cost. Why spend the money on 7 inductors and 2 complex chips if the screen doesn't demand it?
It really highlights the gap between Pro and regular. It isn't just a label on the box or a slightly better camera sensor.
No, the hardware is diverging at a fundamental circuit-level path.
And looking at the trends, we expect this to continue, right? The iPhone 16 Pro, 17 Pro.
As screens get brighter and processors get hungrier, this interleaved architecture is the only way to feed the beast. We might even see more phases added in the future.
Okay, I want to pivot for a minute to the people who might actually be looking at this stuff under a microscope. The technicians, the people who have to fix these things when they break.
The brave souls.
We talked about how hard this is to map mentally with the split brain layout. But let's say I've got the phone open, I've got my multimeter. How do I know if I found this specific VDD SNS BPIC line? Is there a secret handshake?
There is. And it's hidden in the capacitors.
The little ceramic brick things scattered everywhere?
Right. Now, normally when you're poking around the main power lines of a phone, you see a wide range of component ratings. But this specific line VDD generated by this system sits right around 4.0 volts.
Which is basically battery voltage.
Correct. Now, capacitors are rated for safety. If a line carries 20 volts, you need a capacitor rated for 25 or 30 volts so it doesn't explode.
Makes sense. You need headroom.
But on this line, because the voltage is so tightly controlled and stable, thanks to our friend interleaving Apple, uses capacitors rated for 6.3 volts.
6.3 volts? That seems like a really low ceiling. That's barely any headroom at all.
It is razor-thin margins. But it's safe because the system is so precise. And for a technician, it's a dead giveaway. If you are probing the board and you see a cluster of capacitors rated for 6.3 V surrounding those big inductors, you know immediately, I'm at the heart of the system.
It's like carbon dating for electronics. The component rating tells you the environment it lives in.
Exactly. If you see a 6.3 V cap, you know you aren't on a backlight circuit, which would be 20 V or more, and you aren't on a CPU core line, which would be much lower, like 0.8 V. You are squarely on the main interleaved rail. It's a huge clue for navigation on a confusing board.
That is such a cool detail. It's amazing how much storytelling is hidden in these tiny specks of silicon and ceramic.
It really is. The board tells a story if you know how to read the language.
So zooming out, we've gone from it's just a power chip to it's a dual chip, 7-inductor, phase-shifted, mathematically sensing marvel.
It's a mouthful.
It is. But what's the takeaway here? Why should the average listener, who might never open their phone, care that their iPhone has 7 inductors instead of 2?
I think it represents a shift in what we consider innovation. For a long time, innovation was make it faster or make it smaller. Now, innovation is make it flawless. Yeah. It's about the quality of the operation.
Yeah.
Apple is willing to complicate the design massively, making it harder to build, more expensive, and much harder to fix, just to ensure that when you scroll through Instagram or watch a movie at 120 hertz, it doesn't stutter for even a microsecond.
It's the pursuit of invisible perfection.
And it works. You don't notice it.
No.
That's the point. You only notice power delivery when it fails. If the engineers do their job right with all this interleaving and sensing, you just think, wow, this phone feels premium. It feels smooth.
But there's a flip side, right? We touched on it at the start. The complexity.
The variability tax.
Yeah.
Right.
I mean, we joked about the split brain layout, but think about the implications. If I drop my phone and a solder ball cracks under U4000 on the back of the board, and that breaks the communication with U4200 on the front of the board.
The whole system fails.
Yeah.
And diagnosing that, attempting to reball or resolder two chips on opposite sides of the board without overheating the delicate layers in between, that takes a master technician. That is not a mall kiosk repair.
It feels like we're reaching a point where the performance demands are creating devices that are becoming black boxes.
It's the Ferrari problem again. You can fix a 1990 Toyota Camry in your driveway with a wrench. You generally cannot fix a modern Formula One car in your driveway.
Right.
You need a team of engineers, telemetry data, and specialized tools.
And our phones are becoming Formula One cars.
Exactly. We demand 120 hertz. We demand all-day battery. We demand thinness. The engineering required to deliver that makes the device incredibly dense and complex. As users, we have to ask ourselves, is that trade-off worth it? Do we want the smooth scrolling enough to accept that our devices are becoming almost impossible for a human hand to repair manually?
That is the $1,000,000 question, or maybe the $1,000 question, depending on which Pro model you buy.
Very true. The cost isn't just on the price tag, it's in the repairability.
Well, something to think about the next time you swipe up on your Pro phone and it feels like butter. Just remember the 7 little magnetic coils and the split brain chips working overtime to make that happen.
The hidden heartbeat, keeping the dream alive.
Thanks for taking the deep dive with us today. It's been, dare I say it, electrifying.
That was a terrible pun, but I'll take it.
I had to do it. We'll catch you on the next one.
Welcome to The Explainer. Today we're diving into a piece of engineering that's as complex as its name sounds. PP_VDD_SNS BPIC. This is the sophisticated new power circuit you'll find in the latest iPhone Pro models. And trust me, if you're a technician or just love this stuff, you're gonna want to see how this works. All right, here's our game plan. We're gonna start with the why this new architecture even exists. Then we'll get into the nitty-gritty of the 7-inductor system and a really cool technique called interleaving. And finally, we'll get practical with a guide for technicians and look at what this all means for the future. So, first things first, let's dig into why Apple decided to move away from its tried-and-true power management design. What was the problem that needed such a major change for the main power delivery? This right here really tells the story. On the left, you've got the old way of doing things, a single power management IC, which is basically just a tiny chip creating the main power line. Simple. But then, look to the right. That's the new system in the Pro models. It's a whole different beast with 2 main chips and 7 inductors. So that really begs the question, right? Why go from a simple one-chip solution to something this much more complex? Well, it all comes down to one word: power. Think about it. The Pro Motion display is refreshing 120 times a second. Those incredible multi-lens camera systems, they are thirsty for power. And they need a huge amount of clean, stable power in an instant. This new architecture is Apple's incredibly smart solution to that exact problem. Okay, so let's pop the hood and really deconstruct this thing. We're going to peel back the layers on this pretty intricate 7-inductor system.
Yeah, I know. When you first look at the board, this system can seem super intimidating. You've got 2 main chips, U4200 and U4000, and then 7 inductors. Those are just components that store energy, all working in concert. It's a lot to take in.
But here's the thing. When you break it all down, it's actually a beautifully simple 2-stage process. The whole system is designed with a clear, logical flow, all for maximum efficiency and control. It's not as scary as it looks, I promise.
So the whole dance starts with this chip, U4000. Think of this and its 3 inductors as stage 1. They're the opening act. Their job is basically to prep the power and send it on to the next stage for the main event.
That power then gets handed off to U4200. And this chip, this is really the star of the show. It takes the power from that first stage, and with its 4 inductors, it creates the final, super stable power supply that the rest of the phone needs to run. And this schematic just beautifully illustrates how the 2 chips work as a team.
You can literally see the power flowing from U4000 over to U4200, which then creates that final output. It's a completely coordinated and incredibly efficient system.
So, what's the secret sauce that makes this whole system so efficient? It comes down to a really clever technique called interleaving.
Okay, here's an easy way to think about it. Imagine you have a bunch of small, choppy little waves. On their own, they're not very powerful. But what if you could time them just right so they all merge together to create one big, smooth, powerful wave? That's exactly what interleaving does with electricity. It combines several smaller signals, cancels out all the unwanted noise, engineers call it ripple, and creates one smooth, stable, and highly efficient power source.
And this right here is the power of interleaving in action. Look at the top. You see all those messy, out-of-sync signals? That's the ripple we were just talking about. But when you combine them using this technique, you get that clean, beautiful, stable power you see at the bottom. It's a really elegant solution. And knowing how it works is cool, but for many of you, knowing how to test it, that's what really matters.
All right, let's switch gears and get practical. For all you technicians out there, if one of these Pro models lands on your repair bench, here is what you absolutely need to know when you run into this circuit.
Okay, here's the magic number you need to remember. When you put your multimeter on this power line, you should be seeing right around 4 volts. It's going to be close to the battery's voltage, and if you see that, it's a good sign the circuit is doing its job. And here's a little pro tip for you. There's a super easy test point right on this capacitor. It's rated for 6.3 volts, so a 4-volt reading is perfectly in the sweet spot. If you measure something way higher than that, well, you've probably just found your problem.
And one more really important thing to remember, this new system is only in the Pro models. So you'll find it in the iPhone 13 Pro, the 14 Pro, the 15 Pro, and their Pro Max versions. The standard models, they're still using the older architecture.
Okay, let's zoom back out and just summarize what this all means. Why does understanding this one specific circuit matter so much for the future of device repair and engineering?
The bottom line is this. If you're doing high-level repairs on modern iPhones, getting a handle on this new system isn't a nice-to-have anymore. It's absolutely essential. It's a core skill now. So let's just quickly recap the 4 key takeaways. Number 1, the new 7-inductor system is built to handle the Pro model's higher power demands. 2, the interleaving technique is the magic that makes it so efficient. 3, you've got a clear test point, look for about 4 volts. And 4, this knowledge is vital for anyone working on these devices today and in the future.
You know, this new system is an amazing solution for the power-hungry devices we have today. But it really makes you wonder, doesn't it? As our gadgets demand even more power with even greater efficiency, what kind of mind-blowing engineering marvels are we going to be looking at next?